Chapter 13.3 Resistance and Ohm's Law. The vocabulary for this section is resistance, ohm, Ohm's law, conductor, insulator, semiconductor, and potentiometer. The objectives are to explain the relationships between current, voltage, and resistance, to use Ohm's law to calculate current, resistance, or voltage, and to distinguish between conductors and insulators. You can apply the same voltage to different circuits and different amounts of current will flow. For example, when you plug in a desk lamp, the current through it is 1 amp. If a hairdryer is plugged into the same outlet with the same voltage, the current is 10 amps. For a given voltage, the amount of current that flows depends on the resistance of the circuit. Current and resistance. Resistance is the measure of how strongly a wire or other object resists current flowing through it. A device with low resistance, such as copper wire, can easily carry a large current. An object with high resistance, such as a rubber band, will only carry a current so tiny it can hardly be measured. A water analogy. The relationship between electric current and resistance can be compared with water flowing from the open end of a bottle, as shown in figure 13.11. If the opening is large, the resistance is low and lots of water flows out quickly. If the opening is small, the resistance is greater and the water flow is slow. Circuits. The total amount of resistance in a circuit determines the amount of current in the circuit for a given voltage. Every device that uses electrical energy adds resistance to a circuit. This is not true. It depends on how it is added to the circuit. It is a case where the structure of a circuit is what determines its behavior. The more resistance a circuit has, the less the current. That is true. For example, if you string several light bulbs together one after the other, the resistance in the circuit increases and the current decreases, making each bulb dimmer than a single bulb would be. This is true only if you are combining light bulbs in series, which means one after the other, so the current goes through all of them, one after the other. Measuring resistance. The ohm. Electrical resistance is measured in units called ohms. This unit is abbreviated with the Greek letter capital omega. When you see the omega in a sentence, think or read ohms. For a given voltage, the greater the resistance, the lesser the current. If a circuit has a resistance of 1 ohm, then a voltage of 1 volt causes a current of 1 ampere to flow. Resistance of wires. The wires used to connect circuits are made of metals such as copper or aluminum that have low resistance. The resistance of wires is usually so low compared with other devices in a circuit that you can ignore wire resistances when measuring or calculating the total resistance. The exception is when there are large currents. If the current is large, the resistance of wires may be important. Measuring resistance. You can use a multimeter to measure the resistance of wires, light bulbs, and other devices as shown in figure 13.12. You must first remove the device from the circuit, then set the dial on the multimeter to the resistance setting and touch the probes to each end of the device. The meter will display the resistance in ohms, kiloohms, or megaohms. This is a little different than how our multimeters work, and we talked about it in class, so you should know how that works. How a multimeter measures resistance. A multimeter measures resistance by forcing a precise amount of current to flow through an electrical device. The meter then measures the voltage across the device. The resistance is calculated from the voltage and current. The currents used to measure resistance are typically small, 0.001 amps or less, so that is 1 milliohm. Any other current through the device interferes with the meter's readings, and that is why a device must be removed from the circuit to measure its resistance. You can also just turn the circuit off, which counts as removing it from the circuit. Ohm's law. Ohm's law. The current in a circuit depends on the battery's voltage and the circuit's resistance. Voltage and current are directly related. Doubling the voltage doubles the current. Resistance and current are inversely related. Doubling the resistance cuts the current in half. These two relationships form Ohm's law. The law relates current, voltage, and resistance with one formula. If you know 2 of the 3 quantities, you can use Ohm's law to find the third. This is an algebraic model of Ohm's law. It tells you that the current, symbol I, is equal to the voltage, symbol V, divided by the resistance, symbol R. It can also be written in 2 other forms. So you can say I is equal to V divided by R, you can say V is equal to I times R, or you can say R is equal to V divided by I. These are all equivalent representations of Ohm's law. The resistance of common objects. Resistance of common devices. The resistance of electrical devices ranges from small, 1 milliohm, to large, 10 megaohms. Every electrical device is designed with a resistance that causes the right amount of current to flow when the device is connected to the proper voltage. For example, a 60-watt light bulb has a resistance of 240 ohms. When connected to 120 volts from a wall socket, the current is 0.5 amps and the bulb lights up. Resistances match operating voltage. If you connect the same light bulb to a 1.5 volt battery, it will not light because not enough current flows. According to Ohm's law, the current is only 0.00625 amps when 1.5 volts is applied to a resistance of 240 ohms. This amount of current at 1.5 volts does not carry enough power, which we haven't talked about yet. Think in terms of energy, they're related. Does not carry enough power to make the bulb light. All electrical devices are designed to operate correctly at a certain voltage. The resistance of skin. Electrical outlets are dangerous because you can get a fatal shock by touching the wires inside. So why can you safely handle a 9-volt battery? This says the reason is Ohm's law. The reason is not Ohm's law. Ohm's law is a good model that can help show us why we can handle a 9-volt battery but cannot handle the 120 volts that comes from an outlet. Remember, current is what flows and carries power. The typical resistance of dry skin is about 100,000 ohms or more. According to Ohm's law, 9 volts divided by 100,000 ohms is only about 0.00009 amps, which is 90 microamps. This is not enough current to be harmful. On average, nerves in the skin can feel a current of around 0.0005 amps, which is 500 microamps. So 500 microamps is the minimum current that your skin can feel compared to the 90 microamps from a 9-volt battery. You can get a dangerous shock from 120 volts from a wall socket because that is enough voltage to force 0.0012 amps, which is 1,200 microamps, through your skin. That is more than twice the amount you can feel. Water lowers skin resistance. Wet skin has much lower resistance than dry skin. Because of the lower resistance, the same voltage will cause more current to pass through your body when your skin is wet. The combination of water and 120-volt electricity is especially dangerous because the high voltage and lower resistance make it possible for large and possibly fatal currents to flow. Changing resistance. The resistance of many electrical devices varies with temperature and current. For example, a light bulb resistance increases when there is more current through the bulb. This change occurs because the bulb gets hotter when more current passes through it. The resistance of many materials, including those in light bulbs, increases as temperature increases. This is one of the reasons that we call Ohm's law a model, because it only works for materials that have the same resistance no matter what the current is. So it doesn't work to model every single material, but it works pretty well at the currents that we use in class. Conductors and insulators. Conductors. Current passes easily through some materials, such as copper, which are called conductors. A conductor can conduct or carry electric current. The electrical resistance of wires made from conductors is low. Most metals are good conductors. Insulators. Other materials, such as rubber, glass, and wood, do not allow current to easily pass through them. These materials are called insulators because they insulate against or block the flow of current. Semiconductors. Some materials are in between conductors and insulators. These materials are called semiconductors because their ability to carry current is higher than an insulator but lower than a conductor. Computer chips, televisions, and portable radios are among the many devices that use semiconductors. You may have heard of a region of California called Silicon Valley, probably because you live there. Silicon is a semiconductor commonly used in computer chips. An area south of San Francisco is called Silicon Valley because there are many semiconductor and computer companies located there. Comparing materials. No material is a perfect conductor or insulator. Some amount of current will always flow in any material if a voltage is applied. Even copper, a good conductor, has some resistance. Figure 13.14 shows how the resistances of various conductors, semiconductors, and insulators compare. Now, in our model, we assume that the wires in our circuit have no resistance, and we model it so that our battery also has no resistance. So all of the resistance in our circuit comes only from the resistors. And this is a model because it's a simplification. Applications of conductors and insulators. Both conductors and insulators are necessary materials in human technology. For example, a wire has one or more conductors on the inside and an insulator on the outside. An electrical cable may have 20 or more conductors, each separated from the others by a thin layer of insulator. The insulating layer prevents the other wires or objects from being exposed to the current and voltage carried by the conducting core of the wire. Resistors. Resistors are used to control current. Resistors are electrical components that are designed to have a specific resistance that remains the same over a wide range of currents. Resistors are used to control the current in circuits. They are found in many common electronic devices such as computers, televisions, telephones, and stereos. Fixed resistors. There are two main types of resistors, fixed and variable. Fixed resistors have a resistance that cannot be changed. If you have ever looked at a circuit board inside a computer or other electrical device, you have seen fixed resistors. They are small, skinny cylinders or rectangles with colored stripes on them. Because resistors are so tiny, it is impossible to label each one with the value of its resistance in numbers. Instead, the colored stripes are a code that tells you the resistance, as shown in figure 13.15. Variable resistors. Variable resistors, also called potentiometers, can be adjusted to have a resistance within a certain range. If you have ever turned a dimmer switch or volume control, you have used a potentiometer. When the resistance of a dimmer switch increases, the current decreases and the bulb gets dimmer, or the volume gets smaller. Inside a potentiometer is a circular resistor and a little sliding contact called a wiper, as shown in figure 13.16. If the circuit is connected at A and C, the resistance is always 10 ohms. But if the circuit is connected at A and B, the resistance can vary from 0 to 10 ohms. Turning the dial changes the resistance between A and B and also changes the current or the voltage in the circuit. Electric circuits in your body. Imagine you're relaxing on the couch, watching your favorite television show. You're so absorbed in the action that you fail to notice your younger sister sneaking up behind you. Suddenly, she reaches over the back of the couch and touches the back of your neck with a wet, frosty ice cube. Before you even have a chance to think, who did that? Your body springs into action. The ice cube triggers a withdrawal reflex that happens automatically without a conscious decision on your part. A withdrawal reflex happens because electrical signals are sent through circuits in your body. When an ice cube touches the back of your neck, an electrical signal is sent through wire-like nerve fibers to your spinal cord. In the spinal cord, the signal is transferred to nerve fibers that control the muscles in your neck and shoulders, causing them to contract, jerking your body away from the ice cube. All of this happens in a split second. Your body sends electrical signals using specialized cells called neurons. A neuron has three basic parts: the cell body, the long stalk called the axon, and finger-like projections called dendrites. Unlike the components of a wire and battery circuit, most neurons don't touch one another. Instead, as the electrical signal reaches the end of an axon, a chemical is released. This chemical is picked up by receptors on another cell's dendrite. The dendrite then activates its own cell body to continue sending the signal through its axon. Nerve impulse, a wave of electrical changes. A withdrawal reflex starts when sensory neurons in your skin receive some kind of stimulus from outside the body. In our example, the stimulus is a change in temperature caused by the ice cube. That stimulus starts a wave of electrical change called a nerve impulse along the cell membrane. When a neuron is at rest, the inside of the cell membrane is electrically negative compared with the outside. A nerve impulse works like this. 1. The outside stimulus causes the cell membrane to open tiny channels that let positively charged ions into the cell. The inside of the cell becomes positively charged relative to the outside. 2. Other channels open and let positively charged ion out of the cell. As the ions leave, the inside the cell membrane once again becomes negatively charged compared with the outside. 3. The nerve impulse travels down the axon like dominoes falling. When the impulse reaches the end of the axon, chemicals are released and picked up by an adjacent neuron, causing the nerve impulse to continue. Your complex nervous system. The withdrawal reflex takes only a fraction of a second. In fact, the signal travels from the sensory nerve to the spinal cord and out to the nerves that control your muscles at about 250 miles per hour. It is unlikely, however, that the withdrawal reflex would be your only response to the ice cube. Sensory neurons located in your eyes and ears would send messages to your brains as you turn to see and hear your sister scamper away. Your brain processes these in milliseconds, and billions of neurons there are activated as you decide how best to respond. Maybe you feel annoyed and chase after her with an ice cube of your own. Or you might just laugh at the clever way she paid you back for an earlier prank. Your emotions, decisions, and physical actions all happen through nerve impulses sending electrical signals through neurons in your brain, spinal cord, and body. A single neuron can have up to 10,000 dendrites connecting to other neurons, and it is estimated that just 1 cubic millimeter of brain tissue contains a billion connections between cells. Each second, your body fires off about 5 trillion nerve impulses, making it possible all the things that make us human: thoughts, memories, decisions, emotions, and actions.